Okay, so I'll just scan through this NP completeness, right? Yesterday we saw this one. Let me see. I should have these slides. Okay. Okay. Now you can see the slides.
Yes, sir. Yes, sir. It is.
Okay. Okay. So we have already seen this thing, a decision problem. The answer to the problem is either yes or no. Such a problem is called decision problem. And the NP completeness theory is applicable to decision problem, and we can extend it to optimization problem to some extent. So we'll see what it is. Right. So for example, Hamilton cycle problem already we have seen. So the problem will be specified in this particular format, like instance, that is input, a graph is given and you ask a question. And the answer to this question will be either yes or no. So the Hamilton cycle, Turner graph problem, decision problem. So these are basically decision problem. So optimization problem, there are other problems which are called optimization problem, where he asks to find out a value, objective function has to be minimized or maximized. So either is a maximization problem or minimization problem. For example, traveling salesman problem. So you are given a weighted complete graph, and you have to find a Hamilton cycle of minimum cost. And similarly, click problem. So a graph is given, and you want to find a maximum cardinality click in G. So that means among all clicks, you have to maximize the size of the cardinality of the clicks, and that is what you have to see as the click number. So these are optimization problems. Similarly, other graph problems are there which are optimization graph problem, like independent set problem, where you need to maximize the independent set, matching problem, maximum matching problem, shortest path, minimum cost path from source to destination. Then MST problem already we have seen, finding a minimum spanning tree of minimum cost, finding a spanning tree of minimum cost, minimum dominating set. So many problems are optimization problem as well. But the NP completeness theory is applicable only to a decision problem. Last time we saw, but nevertheless, this optimization problem has corresponding decision problem. So for example, decision version of optimization problem, every optimization problem has an underlying decision problem. And so how do you get the decision problem out of the optimization problem? Here we introduce a parameter K, extra parameter K, and ask a question involving less than equal to or greater than equal to, less than equal to for greater than equal to for maximization problem, and less than equal to for minimization problem. For example, you see, just see, it should have been like this, involving, this should have been involving less than or equal to, or okay, this is fine, greater than, for less than or equal to, for since you are going to maximize, so it will be, this will be mean and this will be max. This will be mean and this will be for max. So what is this? For example, let us see. So this click decision problem is a maximization problem. So this was the instance of the only this much was given in the click problem. A graph was given, and we wanted to find a maximum size click. So we introduced a parameter K, and then we ask, so does G contain a click of size at least K? At least K means greater than or equal to K. So for maximization problem, you introduce a parameter K and ask the question, a click size, and then introduce greater than or equal to K in terms of this. If it is a minimization problem, then you ask less than or equal to. For example, dominating set. Dominating set decision problem. So the instance, I can say a graph G, and we introduce a parameter K, and you ask the question, because this is a minimization problem, so it should be less than or equal to at most. Does G contain a dominating set of cardinality less than or equal to K? Is this clear?
Yes, sir. Yeah.
Yes, sir.
So NP completeness deals with decision problem only, but even though optimization problem is there, it will have a corresponding decision problem. And now, if you can show that this decision problem is NP complete, then the optimization problem also will be hard, and that will be NP hard. So we'll see that what is it means. So the verification algorithm that we'll see, efficient verification algorithm. So an algorithm B is an efficient verification algorithm for problem pi if the following property hold. So first of all, B should run in polynomial time, and it should take two input. One is instance of the original problem, and C is a certificate basically. It should be a short certificate because the size of C is bounded by a polynomial in the input size I, right? So it should be a short certificate. And now for every instance I of pi, I is an yes instance. As you say, as we discussed in the last class, we are worried about the input for which the answer is yes. So I is an yes instance if and only if there exists a certificate C, which is short certificate for some constant k. That means it is a short certificate, so that once you give this particular certificate, the answer to this question is yes. So we are bothered about yes instance. If it is yes instance, then you should be able to provide a certificate. And now you should be able to verify in polynomial time that this is a yes certificate. The instance is a yes instance. So last class we saw the efficient verification algorithm. This is a formal definition. And the NP is the class of all decision problems that admits efficient verification algorithm. And what is a certificate? A certificate is a characterizing property, and we are interested in a short certificate. Short means polynomially bounded in the input size. So that is the, for example, graph. Given a graph, now the input size will be n and m, or n is there. So this certificate size should be less than equal to some n raised to power some constant k. K is a constant, right? And pi is the set of all decision problem that admits polynomial time algorithm. So we saw that the P is a subset of NP. So that means if you know how to solve the problem, we can verify that it is a yes instance also. So pi belongs to P. So you design this algorithm B of I comma C, and just you run this algorithm A, which is a polynomial time algorithm to solve the problem pi. So for example, MST problem, for example, this particular problem. So your graph G is given, weighted graph, and you are asking the question, does G contain a spanning tree of weight less than equal to M? G and M is given, a real number given, right? R plus. So we know that this minimum spanning tree problem can be solved in polynomial time. So now we saw that this problem belongs to NP. What you do, given a graph and a real number M, we just run the minimum spanning tree algorithm, and then you check what is the weight of the minimum spanning tree. That weight is less than equal to M, then we return yes, otherwise we return no. So without using any certificate, so we ignore, even if the certificate is given, we ignore it, and then we run the algorithm that solves the problem in polynomial time, and whatever based on the answer, we give the answer whether it is a yes instance or no instance.
So here what here what is the certificate, sir? Here M is certificate,
So,
right? Or
and for example, for example, see, as I told you, right? If you say that you are a student of IIT Delhi, and if I have the list of all the students, so whatever ID card or whatever certificate you give, I don't want to see this also. I will see my master list and I verify.
Okay,
but your claim is true. If it is a true instance, then I can verify in polynomial.
Right. Okay.
So that is basically ignore the certificates.
Yeah. Okay.
So P is a subset of NP. So the question is, so for example, Hamilton cycle problem we have seen in the last class. So given a graph, So the certificate will be a permutation of n vertices. So we need to check that these vertices are distinct, and then the consecutive vertices are adjacent, and then first and last vertices are also adjacent. So you can see this particular code can be checked in polynomial time. So if this is the case, then we can return that it is yes. So if the graph is Hamiltonian, there will definitely exist such a permutation. And if graph is not, so we are bothered about, if graph is not Hamiltonian, we are not bothered about that. If the graph is Hamiltonian, then you should be able to get a certificate. And now using this, we will be able to verify in polynomial time that this is a yes instance, that means it is a Hamiltonian graph. So this part showing it is in NP is generally easy. But okay, so this is what we saw in the last class, polynomial time reduction. So polynomial time reduction is a function from f from instance of first problem to instances of second problem, satisfying these two property. F can be computed in polynomial time, and it preserves the yes instances. For example, I is an yes instance of pi1 if and only if this fi is an yes instance of pi2. So, so for example, we saw that independent set decision problem is polynomially reducible to clique decision problem. So what are the transformation that we saw? Given G and K for ISDP. So how do you get this function f? We got G dash and K. What is G dash? G dash is equal to G complement. So this is my f. So given a graph and an integer K, that is an instance of independent set decision problem. So we construct the G complement and then K. And we know that S is a clique, S is an independent set of G, if and only if S is a clique of G complement. So if this instance is an S instance, that means it has a independent set of size greater than or equal to K, then the same set will form a clique of size greater than or equal to K in G complement. So the second property is now true. And given a graph G, we can compute the G complement in order of n square time at the most, right? So this can be computed in polynomial time. So this shows that ISDP is polynomial time reducible to clique decision problem. And then independent set decision problem also is polynomial time reducible to vertex cover problem. So what is vertex cover? Vertex cover means a set of G is given, G is equal to V, comma E is given. S subset of V is a vertex cover if every edge XY belongs to E, X belongs to S, or Y belongs to S. That means the set of vertices is going to cover all the edges. So for example, I'll take one example. For this graph, what is the vertex cover? What are the vertices we have to select so that all the edges will be covered? Can somebody tell? Suppose if I take this particular vertex in the vertex cover, right? So which edges are covered by this vertex? So this edge is, this what edge is covered, this edge is covered, this edge is covered, this edge is covered. Now it remains only two. So which is the second vertex we will take?
Opposite corner.
Opposite vertex. So if you take this vertex is covered, this edge is covered, this edge is covered. So that means these two vertices will form a vertex cover. So now the question is, now given an integer K, is there any vertex cover of cardinality less than or equal to K? So you see this is a minimization problem. So here the question is less than or equal to K, and here you will be asking for greater than or equal to K. And K dash. So how do you find that independent set decision problem is polynomially reducible to vertex cover decision problem? Anybody who knows some graph theoretic characterization? So there is a suppose S is an independent set if and only B minus S is a vertex cover. So this is a simple result of graph theory. S is an independent set of G if and only the remaining vertices B minus S is a vertex cover of G. Because if it is an independent set, so no edge is there. So this is B minus S. So every edge will have like this or like this. So every edge will have an endpoint in this particular set. So B minus S will be a vertex cover. So now you tell me what should be the function that we find out in the polynomial reduction. Gavaskar.
Sir, the
question is, this independent set decision problem is polynomially reducible to vertex cover. So this is the result I have given, hints I have given. So given a graph and integer k, what should be my graph for the second problem and the integer k? That. So what is the result?
Minimum. Yeah.
So for example, S is an independent set of G if and only V minus S is a vertex cover of G. So given G and K, this is independent set problem instance. So we construct what? G and N minus K. My K dash. K dash is this N minus K. So G has a vertex cover. G has an independent set of cardinality greater than or equal to K. So G has an independent set of cardinality greater than or equal to K if and only G has a vertex cover of cardinality less than or equal to N minus K. So that is K dash, right? So I need not have to do anything. Given the graph, I produce the same graph, and instead of K, I take N minus K. So that is an instance, and this is my function F. So you know that this can be done in polynomial time, and it satisfies this thing. This is an ES instance. That means it has an independent set of cardinality greater than or equal to K. Then the same graph has a vertex cover of cardinality less than or equal to N minus K. So this is a polynomial reduction. So what is the meaning of this polynomial reduction? If you can solve this particular problem in polynomial time, it belongs to P, implies ISDP in ISDP belongs to P. So the easiness goes in this direction, easy.
Okay, this particular problem, sir, this reduction, above reduction. So F defined G to G itself, right? So there, how we can check F is polynomial reduction?
Polynomial reduction means what? Okay, this is basically given a graph, you have to construct another input. I am not doing anything. Just I have produced the same thing, and instead of K, I'll write K minus 1. So only one step I take. Right?
Okay, so order of 1, right?
Order of 1. In the first problem, G, I found out G complement. There I have to do something. Order of n square, right?
So
that is how you do. So some problem it is very easy, some problem it is very difficult.
Okay,
right? Okay. So NP completeness, we have seen a problem pi is an NP complete if pi belongs to NP, and every problem in NP is polynomially reducible to this. That means for all pi dash belongs to NP, pi dash is polynomially reducible to pi. But we do not know how many problems in NP are there. So this is, though it is a original definition, using which it is difficult to prove. So we need to see something else. So if this condition is there, for example, a decision problem is NP hard, if you are not able to show the first property, that is pi belongs to NP, you are not showing, but only the second property you are showing reduction. Every problem in NP is polynomially reducible to pi, then pi will be NP hard.
Here one small question. Sorry, sir, I'm asking.
Okay. Oh, sure.
See, I need an NP complete problem, but satisfying first property, but not satisfying second property. Such a problems are there?
What?
We need an NP complete problem
Okay.
that satisfying first property, that not satisfying the second property.
No, NP complete means it has to satisfy both the property, right? Then only call it is NP complete. There is a
No, see,
definition.
that means say, so the less than pi dash less than or equal to say p pi. So no such a pi dash if it is exist, then in that case, can you say that there is an NP complete?
No, you have to show there should be one problem, like
At
all
least
the
one
problem.
No, maybe same problem.
We have
Worst
not come to that definition. We have not come to that definition. This is that for all pi dash in NP, pi dash is polynomially reducible to pi. So though it is a definition, but it is not a working definition. So we'll see in the next slide what is the working definition of NP completeness.
No, the worst case, yeah, pi equal to pi dash, maybe we can take that satisfying the second property. Can you say?
No, but then pi, this we are going to show that pi belongs to NP, right? Pi, so it is for all. It is not for only one. It is for all. Every problem in NP is polynomially reducible to pi. That we have to show from this definition.
I ask the thing is no problem in NP that is polynomial reduction to pi. So that problem is NP complete.
No. So see, for example, how do you show that a polynomial reduction doesn't exist? It's so many, right?
Okay.
If you can, okay, right?
No, I'm practically so. Not, maybe.
No, to show NP context, this is the definition. You have to show that every problem is NP.
Okay, otherwise we cannot say, right? Okay.
Okay. So okay. So what basically the moment you prove that the problem is NP complete, so what it does and what it doesn't. So NP completeness doesn't provide a method of obtaining polynomial time algorithm for the second category problem. That is NP complete problem, right? Doesn't provide any polynomial time algorithm, and it doesn't tell that polynomial time algorithm for this problem do not exist. So neither it tells that the problem is not solvable or the problem is solvable. So there will be a qualification, that means under P not equal to NP, NP complete problem doesn't admit polynomial time solution. That much we can say. So by showing just the problem is NP complete, it doesn't tell anything that it is a hard problem. It hard problem provided P not equal to N. So that is what it says. Then one has to remember. And does show that some of these problems for which no polynomial time algorithms are known are computationally related. So if we have already seen that the pi1 is polynomially reducible to pi2, and pi2 belongs to pi2 belongs to P, implies pi1 also belongs to P. But the moment you show that these are polynomially equivalent, so both will admit polynomial time solution or both will not admit polynomial time solution. They are polynomially equivalent. Okay, so let me see. Okay, so there is a problem called satisfied problem. So that this problem was shown to be NP complete. This is the first problem which was shown to be NP complete using this definition. So this definition using, that means every problem in NP is polynomially reducible to set. That is the first problem which was shown to be NP complete. So what is this set problem? So set problem is a Boolean variable is a variable that can take the value 0 and 1, and literal is either x or its x complement, a complement or the Boolean variable. So this is basically literal, and a formula consists of literals and operators and or operator, these two operators. And so for example, I can see formula f is x1 or x2 or x3 complement. So this is a formula. This is using or operator, or I can use an AND operator also, x4. So this is the or operator and this is the AND operator. So this is a formula. But the CNF formula is conjunctive normal form formula. Conjunctive normal form. CNF formula, that if every formula uses only a formula that uses AND operators and clauses, and each clause is constructed using or operator. For example, F I can write as C1 and C2 and C3. So this is the using AND operator. I am using clause C1, C2, C3, and C1 must use only AND operator, say X1 or X2 or X3 bar. C2 is equal to X2, X1 complement or X2 complement or X3 like this. So another thing is that given any formula, it can be converted into CNF formula. And now the set problem is given a CNF formula F, is F satisfiable? Satisfiable means a formula is satisfiable if there is a truth assignment that assigns truth value T or F to variables such that the formula evaluates to be true. For example, in this formula, so for example, only C1 and C2 is there. Then if I assign X1 is equal to true, X1 is equal to 1, and X2 is equal to 1, and X3 is equal to 1. So whether this formula will be true or not, X1 or X2 or X3 bar, whether this C1 will be true or not. X1 is 1, that means true, X2 is true, and X3 is also true.
Yes, true.
This is true, and similarly, this is also true because X3 is true. X3 is true, so this is true. So true and true is true. So that means this particular assignment, X1 is equal to 1, X2 is equal to 1, X3 is equal to 1, will be a truth assignment for F. That means F will be satisfiable assignment if I assign X1 equal to 1, X2 equal to 1, and X3 equal to 1. So by the way, you have n variables are there, Boolean variables are there. So how many truth assignments are possible? F is from what? F is from X. Every element of X will get either 0 or 1. So n variables are there, so it is going to get how many 2 raised to power n such formulas are there. So truth assignments are there, isn't it?
Yes, yes.
Yes. So now question is, given a formula in CNF form, is F satisfiable? This is a decision thing. Does it belongs to NP? Can you tell what will be a certificate for this thing? Suppose this formula is satisfiable. So what will be a truth assignment? What will be a certificate?
The assignment maybe.
A truth assignment is a certificate. So given a truth, you suppose you claim that this formula is true and you provide me a truth assignment, just I have to verify like this. For example, X1 is equal to 1, X2 is equal to 1, X3 is equal to 1. You say that for this particular formula, this is a satisfiable truth assignment. What I did, I just substitute in these clauses and see that each of the clauses is true, because the clauses are now combined using AND operator. So the formula will be true if and only each of the clauses will be true. So I can check in polynomial time. So this set belongs to CNF, belongs to NP, like set problem belongs to NP. Is this clear?
This problem, satisfiable problem is this is for every assignment or
no. Does there exist an assignment, truth assignment? Satisfiable means a formula is satisfiable if there is a truth assignment.
Okay,
at least
okay,
one
yes,
truth assignment.
Yeah. Okay,
Right?
okay, yeah. Oh, that is mentioned in the definition, right? Sorry.
Yeah.
Right.
Okay.
Okay.
So this belongs to NP, but this important thing is that the first NP complete problem was shown by Cook and Levin. This is the Cook-Levin theorem. Set is NP complete. That means every problem in NP is polynomially reducible to set. So now, since once we got the NP complete problem, and this relation is a transitive relation. So pi1 is polynomially reducible to pi2, and pi2 is polynomially reducible to pi3, implies pi1 is polynomially reducible to pi3. So suppose this is a f is the reduction over here, g is a reduction over here. So what will be the reduction from pi1 to pi3? G of f. Right? The composite function g of f will be a reduction from pi1 to pi3. So this will be a this relation is a transitive relation. And now based on this Cook-Levin theorem, now this is a working definition of NP completeness. So what is that? The first condition is same. That means pi belongs to NP. And instead of now reducing every problem in NP, only you have to look for one NP complete problem. So once you find a NP complete problem pi dash, and only one problem you reduce it to pi, that means pi dash is polynomially reducible to pi, then you are done. So at least we have one in the bag, that is set. And now you have got thousands of problems or several thousands of problems are NP complete. So to show a new problem to be NP complete, you can choose one problem and NP complete problem. And first thing you show that your problem is in NP, and choose an NP complete problem and show that it is reducible to your problem. Is this clear?
Yes, sir. Yes, sir. Yeah.
Okay, so we'll give one example of NP complete problem. So for example, this is a problem which doesn't belong to NP that you are talking about, right?
Yeah, yeah.
So halting problem is a problem. Given any arbitrary deterministic algorithm A or algorithm and an input I to A, decide whether A will terminate on I. So for example, is it possible that, for example, I have given some programming assignment to solve a problem, right? So people have given this program P1, P2, PK. So K students are there. They have produced the program P1, P2, PK. So I have to check whether this program will terminate when X is given the input, whether this program will terminate or it will get into infinite loop. I want to check. So instead of checking each of this program, can I write a program P which will take this Pi and X and return 1 if Pi terminates, else 0. Pi doesn't terminate. Can I write such a program P or maybe Q? Such a program, can I write a program which will take input as a program and input to this particular program and will tell whether the P1 is going to end or it is going to run forever. So is it possible? That means whether P1 is going to halt on X or it will not halt on X. Can I write such program? So such a program, if you can write, that is called, this problem is halting problem. So this, it is shown that this halting problem doesn't belong to NP. So this is a, so the answer to this problem is either yes or no. So it is a decision problem, but halting problem is the one problem which is shown that it doesn't belong to NP. Right?
Yes, sir.
Okay, so you can see the slides. It's not that difficult, but only one. Okay, so this is how we will show that the NP completeness. One problem I'll show and then I'll stop. I'll go to the assignments, tutorials. That click decision problem is NP complete. So we have already seen that CDP belongs to NP. So first condition I can show that CDP belongs to NP. Click decision problem. What is the certificate for click decision problem? A subset S, right? And I can check that the subset is a click or not, and size of this subset is greater than or equal to K or not. So this can be verified in polynomial time. So the CDP belongs to NP. This is the first condition. Now we know that set is NP complete. So we get a polynomial reduction from set to CDP. Now we can check. We are not talking right hand side, we are talking about a graph problem, and left hand side we are talking about a different problem. Right? Okay. So given an input for set satisfiability problem, now we'll construct a graph in such a way that the set is satisfiable if and only if the constructed graph has a click of size greater than or equal to K. So, let C1, C2, Ck, these are the K clauses of an instance of set. So your formula F is equal to C1 and C2 and C3 and Ck. And each of the clauses CIs are made using OR operator, using the variable and their complements, right? So we construct a graph V, E, where the vertex sets are the order pair sigma, I, where sigma is a literal in the clause Ci. So for each clause Ci, we take Ci has got say 5 literals, so I will have 5 vertices. Sigma literal, I, first literal, I, second literal, I, third literal, I, and fifth literal, I. So these are the vertices. So how many vertices my graph will have? Vertex set is equal to same thing as summation of Ci cardinality. I is equal to 1 to k, right? Because each clause is going to give rise to how many vertices? The size of the clause. So how many literals are there? So that many vertices will come will be contributed by this particular clause. So I have the vertices, and now I have this order pair where the first one is a literal and second one is the clause number. So the E is basically from these two order pair they are adjacent. If they do not belong to the same clause, that means I not equal to j, and one literal, that sigma literal is not the complement of the beta. Is this clear?
For
Yes
three
or no?
circuit, yeah, the
Okay.
three
So,
circuit,
I
for
should
three,
have let me see, I should have an example first. Let's see. If example is there, I'll just say. Otherwise, I'll construct an example. Right. So let me construct an example. Right. So this, for example, so my F is equal to C1 and C2 and C3. C1 is equal to X1 or X2 bar or X3. C2 is equal to X1 bar or X2 bar or X3. C3 is equal to X1 or X2 bar or X3 bar. Right. So 3 clauses are there. So in that case, what will happen? I will have 3 set X1, 1, X2 bar, 1, and X3, 1. So this is in one set. Then X1 bar, 2, second clause, X2 bar, 2, X3, 2. This is the second set. This is my second set. And X1, 3, X2 bar, 3, and X3 bar, 3. So these are the third set. So these are the vertices, 3 into 3, 9 vertices. And what will be the edge? So for example, X1, 1, X1 bar, 2. Will there be any edge or will not be any edge? The second component 1 not equal to 2, that is fine. But the X1 is equal to X1 bar bar. That means so there cannot be any edge from this vertex to this vertex. But this to this there is an edge. This vertex to this vertex there is an edge. X2 to this there is an edge. X2 to second there is no edge. And X3, this is there is an edge, and there is an edge. So you can compute the other edges. Is the construction clear? Yes or no?
yeah, for me, okay, sir.
Okay. So basically, this is what? Yeah, this is the definition, right? So already once this edge set is given, then you should be able to construct the graph based on the particular example. So now this construction can be done in polynomial time, and now we'll claim the following: F is satisfiable if and only if G has a clique of size at least K. So you can see this thing that these sets, the vertices which are coming from the same clause is an independent set. This is an independent set. So this is an independent set. So this graph is decomposed into k independent set, at least k clauses are there. Now, at what can be the maximum click? A click can come from each partition can contribute only one vertex because it's an independent set. So click size can be at the most k. So, but click size is k if and only if it is satisfiable. That is what it is proved. So assume that f is satisfiable. So each clause ci has a two literal sigma I. So then you construct the clicks sigma I comma I from each clause. That true literal you take under the truth assignment, whichever is getting truth value t, that literal comma this clause number they collect it, and these are basically coming from different clauses, and since they are getting the truth value t, so one cannot be the complement of the other, because one is complement of the other, one is getting truth value t, the other one is get the truth value f. So that cannot be the case. So S will be forming a clique. So S forms a clique of size k. And now suppose G has a clique of size S, then at least k, that means those literals sigma i's you assign the truth value t, and other you give the compatible, extend this truth assignment to other variable. And now that will become a, because each clause you are giving only at least one variable, the truth value t, that assignment, truth assignment will be a satisfiable truth assignment. So this f is satisfiable if and only if G has a clique of size at least k. So since we are proving this thing, this problem is in NP, this problem is NP complete. So this is how you have to show, though the set and clique are unrelated problem, but wherever you can define a binary relationship, that means the literal belongs to the clause, that is the belongs to the relation. Using this kind of relation, you can always construct a graph. So this is how you can show a new problem to be NP complete. Is this clear, Gavaskar?
Yes, sir. Yes, sir. Yes, I see how they are related.
Yeah.
The graph generation is very important.
Yeah. So the more and more, for example, the slides will contain something, and then basically the other problems, similar problems are there. But if you see, so this is basically Bible of this NP completeness. Computers and Interactability, a guide to the theory of NP completeness. The Gary and Johnson had written a book on 1979, and Johnson maintains a website of NP complete problem. Now you can see whatever practical graph optimization problem you can see. So those are all NP complete problems. Optimization problem are NP hard problems. So this is the book which is available also freely in web. So you can download and then see. But another book that you can see is the following. This is the book. This is chapter 8. If one can read this thing, chapter 8 of this particular book is very nicely written book. So this lecture note and chapter this 8 will do the wonders. So you'll be able to start, because several, at least 20 problems, graph problems are given in this book, in this chapter. And those are, for example, coloring, 3 coloring problem is NP complete, any coloring problem, K coloring problem, K greater than equal to 3 is NP complete. So those are very nice thing. And this is one book, unfortunately it is, I don't know how many people will have access to this book. This is the book that one should read if you want to do a graph algorithm research. Applied and Algorithmic Graph Theory by Chatran and Ollerman. This is out of print book, right? And you will not find in the net even. Only few places in India you will find this book. This is a good book to start with. If you start this book, after that one can read the other books. For example, this Introduction to Algorithm, this book will have 1/3 of this book is graph algorithm. 1/3.
Okay.
1/3 of this book, it is a 1,200 pages book, around 300-400 pages are graph algorithms only. Right? So one can start any of the things. And here also several graph NP complete problem, original NP complete problems are given over here. And now this Johnson maintains a website. You can check, you'll find, and there is a website called, if you type in Google graph classes, right? So let me, okay, graph classes, then all these special graph classes will see and what kind of problems are solved, which are not. Let me check if it is, I can find this one.
Which book is good for the beginners level? Like we want to start with the this algorithmic graph theory. So which book will you recommend?
Okay. Okay. So algebraic graph theory, this is the book, but I don't know whether you'll be able to find this book or not. The last book. As I told you, this is a book. Other thing that you can see, some part of this particular book also you can see. Right. Chapter 8. But basically, you know, other books are computers written by computer scientists. You know.
Okay. Yeah,
so, but this book is written by mathematician. Right.
Okay.
So mathematician will definitely find it. Otherwise, computer science will find in this book, and other book will be fine. But the first book you should read it also very nicely. You see this kind of book, earlier it was written. Each line, you know, it's a you'll get a philosophy of each lines, each sentences. So this is a very, very important book and good book to read. And this is the book.
Is it available online also?
This book is available. This book you can find in the Google. You can download also, free copy. But the only thing is that if you start with a bad book of graph algorithm, you'll never learn. That is I can guarantee. Right? Very badly written, many of the books. So if you start with a bad book, it will be difficult. These books are good, but only thing I think you require some other knowledge, and only you can get into the book.
Okay.
Right.
So Garman also, what you are saying, that is computer science people.
What?
The Garman second book.
Second book, that you can go after something. But if you have seen this MST algorithm from my lecture notes, then you can go and see this. There is a chapter called greedy algorithm where MST also has been covered. So that is in same lines, you know. So you will be able to understand that particular thing. But basically, you know, because I had short time to prove the correctness, so I use something called safe edge, right, and a COT concept, COT, and then safe edge, right. But basically these are natural way to prove Prim's algorithm and Kruskal's algorithm by method of contradiction. And you can possibly see my website. Some lecture notes are already uploaded, right, where the proofs are, you know, more graph theoretic than the proof you will find in these books.
Okay.
Okay. So, but anyway, you can write mail giving the reference that okay, you have attended this MIT school, this refresher school. So if I can provide you some material if you require. Okay. And then, as I told you, the IIT Delhi has a summer faculty fellowship program. So next March it will come again, the advertisement. If you come and then work for 1-2 months, then you can start doing research in this particular area also.
No, hardly we are 2 months there. That's what
2 months will be good enough. 2 months will be good enough.
Okay, sir. But 2 months we have to stay in the
campus. Need not. You can come and have 1 week and then go, and at the end you can come back.
Oh, right? Okay. Yeah.
2 weeks will be good enough. 2 weeks will be good enough. Only thing one has to be in touch, right?
Okay, sir. Yeah.
Okay, so that is the thing. So though I know it takes 3-4 classes, in fact 4-5 classes, and a graph algorithm, all maybe 20 NP completeness problems are proved. Then you learn the NP completeness. You can really do the research in proving a new problem to be NP complete, right? Okay. But this is a starting point, so you can take it forward. This is very lucidly written notes, and then basically this chapter 8 of this particular book you can read also. This is a very good book, graph theorist also can now read properly. Though it is written by a computer scientist, very nicely written book. This is Klenberg book. Okay.
Okay, sir.
So now we'll come back to the tute sheet, right?
Yes.
So tute, so did you solve some problem? So this is the tute sheet, right?
Participants, have you solved?
So this one I'll.
You have
see.
any difficulty in any question in tutorial sheet 1 and 2?
So did you try, or shall we try something? Tute one, okay, tute two is there.
I
but
think so. Last one and last one is tutorial 2. and-
tutorial, yeah, second one is tutorial 2.
And
So
last one is tutorial 1. Maybe.
no, tute one, but the tute one, let me see this thing. I should get that particular tute one. No? This is tute one. This is tute one. Okay. Let me save it and then save file. Okay. Can you see this slides? Or maybe I'll again will open it.
Yes, sir. Yes, sir. That.
Tutorial. Where is the tutorial? Tutorial. It's not coming. Where is?
Sir, below one maybe tute 1 and tute 2.
No, not tute one. Tute one. This is okay. Okay. This one we did in the class, right? Yes or no?
Yeah, yeah.
Yes.
Yes, sir.
Yes.
Yes,
Because
sir.
this one we used what pigeonhole principle, right? So you have got degree can be if it is 0,
Yes,
degree
yes.
is 0, then it cannot be n-1, and it is n-1, it cannot be 0. So degree of a vertex belongs to 0 to n-2 or 1 to n-1. So n-1 distinct degrees are there and vertices are there. So by principle, pigeonhole principle, at least two vertices should get the same degree, right? Okay. What is the maximum number of edges of a graph of order n? At least the other participants should tell now, not our
NC2.
sir.
NC2.
NC2. Very good. And choose 2. Right. Okay. See, let P be an integer such that P lies between 0 to n. Does there exist a graph having exactly P odd vertices?
I think no.
No for what? If P is odd, right? Exactly P odd vertices, right? Having exactly P odd vertices. Does there exist a graph having exactly P odd vertices? P is odd, and then you cannot have odd number of odd degree vertices are not possible. But P is even, you may have this one, right? For example, P is equal to 2. P is equal to 2. So what you can do, for example, I can have a cycle. So this is basically cycle and exactly 2 vertices of odd degree. So this is 3, this is 3 and other are 2. So you have to construct given these values. So when P is odd, so you cannot have other cases now. You can have the graph. For example, see, there cannot be odd number of odd degree vertices. So what about cases when P is even? P is even, you have to construct basically. So, okay. So a graph of order 20, order means number of vertices, size means number of edges, 50, and has 12 vertices of degree A and remaining vertices of degree B. Find the possible values of A and B. So how do you approach?
Sir, Can you approach in this way? Suppose sum of the degree of vertex is twice of edges.
Yeah, very good. That is the
So therefore we can write down, suppose 12a plus 8b equals to 2 into 50.
okay. Very good. So
Then
12a plus remaining is
8b
8b is equal to
8b
50.
equals to 50.
50.
No, 2 into 50
No,
means
no,
100.
so 100. Very good.
100. Yeah.
Size
So
is-
from that we have 3a
so
plus 2b
3a plus 2b is equal
2b
to
equals to
25.
25.
So,
So it has a singular one solution we have. Suppose a equals to 3 and b equals to 16.
a is equal to 0, so you cannot have
So
right?
a equals to 3, a equals to 3 and b equals to 16. We have one particular solution.
one particular, but a, so now what happened? 12 hai, so degree can be lies between 0 to n minus 1, right?
Yeah.
So a can be without loss of generality, a is less than equal to b. You can see that you vary a and then you can find out for which values of a. Now the other one will be possible. For example, here, right? So possible cases is a is equal to 1, b is equal to 11, a is equal to 2, not possible, a is equal to 3, and b is equal to 8, a is equal to 4, not possible, a is equal to 5, b is equal to 5, and a is equal to 6, not possible, a is equal to 7, then b is equal to 2. So b, okay, so up to this you are there. After that, you will not be able to have. Right?
Yeah.
So this is end cycling lemma, basically application. So prove that either G or G its complement is connected. That we did in the last class, right? Last class. Yes?
Sir.
Okay. So this student sheet anyhow, I'm sharing the solution. So you can see what whatever I have already done, I'm not going to see again. Ajay. Let G be a graph containing P vertices of degree P and Q vertices of degree Q. And P plus Q is equal to N. If G contains an odd vertex, then prove that every vertex of G is odd. This also we saw, right?
This you have done the class. Yeah.
Yeah, we did in the class, right? So this, because this is here only thing, odd number of vertex is not possible. That is the key in proving this particular problem. For example, this is a case. So Q is odd. We get Q square is odd. So Q is odd. Since the degree of each vertex of G is either P or Q, every vertex G is of G is odd. That you have to prove. Okay. Prove that a k-regular bipartite graph has no chord vertices. Bipartite graph is this. Two parts. Suppose it is two regular, then I can have something like this. This is a two regular. Degree of each vertex is 2, and this is a bipartite graph. Now this graph has no chord edge means after deleting this edge, now you will not be having the chord edge means after deleting the edge, the graph becomes disconnected. So you say that k-regular bipartite graph has no chord edge. How do you prove? So can you show that this the graph is k-regular bipartite graph, then cardinality of x is cardinality of y? How do you show that? Yes?
There must be a bijective map.
No, not bijective. So k-regular means
One.
each vertex, how many edges are going from x to y from each vertex? K vertices.
K-regular मतलब all degree same.
So all degrees are same. So number of edges going from x to y is k into mod x, and number of edges going from y to x is k into y. So these two are same, and k is greater than k is non-zero. So I can got it. So mod x equal to mod y. But now there is no cortex. Now you can see this thing. Suppose there is a cortex QV. After removing, the graph becomes disconnected, and you have got two graphs, G1 and G2, two connected components obtaining after this thing. Exactly one or V will belong to G1 and the other will belong to G2. Why? So it cannot be this thing. Suppose these are one component, this is another component. So U will be here and V will be here. It cannot be that U, V will be in the same thing, because after deleting only, the graph becomes disconnected. So U and V will be in different components. So number of edges incident on the vertex in X1 is equal to number of edges incident on the vertex Y1. For example, in this case, now exactly one of you will be, okay. So number of edges incident on the vertices in X1 is equal to number of edges incident on vertices Y1, and degree of each vertex in X1 is K, except this particular vertex, because this degree is K minus 1, this degree is K minus 1, others will be degree will be K. So now what you can see that how do you do that? Okay. So degree of each vertex in Y1 except V is K, and degree of V is equal to K minus 1. So total number of degrees over here is basically Q minus 1. The number of vertices is Y is Q. So Q minus 1 into K plus K minus 1. So degree of this vertex is K minus 1. And X1 has P vertices. So X1 is X1. For example, this is a claim that Q and V will belong to G1 and the other will belong to G2. So this is the case. We prove, so it cannot belong to the same vertex. If it belongs to the same thing, then we have a contradiction. So it should be worse. No. So how do you prove it? Basically, just see one second. So this graph was like this, right? And X, Y is an edge. After deleting, the graph becomes disconnected. So once you do this particular thing, so this is my X, this is Y, this is Y, this is Y. So after that disconnection, what will happen? So this will be this graph, two components. Again, this subgraphs also will be bipartite, and then something like this, something like this, and this where this new edge will be there. So the edge XY will belong to where? Tell me. After deleting, this graph becomes disconnected. So this XY edge is suppose the pot edge. So where, from which part to which part this edge will be there? Either this. So without loss of homogeneity, it will be like this. So now all these vertices except this and this after deleting will be K minus 1. This will be also K minus 1. So look at this particular graph. So the number of vertices over here is say Q1 and this is P1. So total number of edges going from here to here, or maybe, okay, going from here to here is K into Q1, and this is K minus 1 into P1 plus K minus, sorry, it will be what? Except one vertex, the remaining vertices, suppose this has got P1 vertices. So P1 minus 1 vertices are degree K, and one vertex is also degree K minus 1. Because if you remove it, this vertex is degree K minus 1. Here all the vertices are degree K1. So P minus 1 into K plus K minus 1 is equal to K into Q1. So that is basically which has been done. So Pk is equal to this. LSH is divisible by K, but RHS is not divisible by K. So we have a contradiction. So there cannot be any cottage. Is this clear? Yes or no?
Yes, sir. Yes, sir.
Yes, sir.
Okay.
Sir,
Okay.
sir, you have written is above.
Yes. Okay.
Uh, if one, suppose if you consider 3 regular graph,
Okay.
then if you remove your 4 regular graph, suppose if you remove one is, then how it is disconnected, sir?
No, that's what we are getting a contradiction. It is in case it is disconnected, then you'll have two components, and we are getting a contradiction.
Okay.
So
Fine.
we are showing that there cannot be any cottage.
Okay, fine.
Okay, but 3 regular graph can have this thing. For example, 3 regular graph can have a cottage. For example, something like this. Let me take one example. If it is not bipartite,
only one.
no, bipartite graph is basically that is the extra thing which is given, right? For example, here I can have 3 regular graph. How do you construct?
Regular graphs, it means three vertices both sides and then connect to 3 edges.
Okay, now that is 3 regular I can have. You want to have a cottage, something like this, and then
What example, sir? Example?
no.
3 regular graph,
3 regular
bipartite graph.
bipartite.
No, bipartite graph. 3 regular graph having a cottage, something like this. So this can be a cottage.
Tattoo graph. Tattoo graph.
So 3. No. This is basically.
No, sir, this will mean,
So this is basically, this is not there. So this is 3, 3, 3, 3, right? So this will be, just a minute. So this is 3, 3, 3, 3, 3. So similarly, here I'll make it 3 regular. This is a 3 regular graph. So bipartite is not there, then you can have a cottage. 3 regular graph, and then you can remove this one. This is a cottage.
The middle, yes, sir. This,
Middle edge.
then this.
But it is a bipartite graph. K regular, this bipartite is important because then only you can have equal number of vertices or number of edges going from one part to the other part. You can argue, but this will not be extended to other graphs, right? This is a counter example. A 3 regular graph can have a cottage. Is this clear?
Yes, sir.
Okay. So we are here, right? Okay. Let G be a graph with at least 2 vertices. That is non-trivial graph. Suppose if you delete a maximum degree vertices, cannot increase the average degree. What is the average degree? The sum of di, I is equal to 1 to n divided by n is equal to average degree.
Yes, sir.
Average degree must be less than or equal to delta G and is greater than or equal to small delta G.
A small delta G minimum.
Okay. So in the graph, you are now removing a vertex of maximum degree. So will that so this statement that it cannot increase the average degree. So average degree will not increase after deleting a maximum degree vertex. Is this true or not? And similarly, deleting a vertex of minimum degree cannot reduce the average degree. This is against the intuition, right? So 10 numbers are there, its average is 5. And maximum number, if you take it, say 20, if you remove 20, the average will come down. But this says that the average degree will not, cannot increase. So it is coming down. Basically, it is giving, this is, in line with the intuition, right? So for example, 2, 5, and 10 are there, right? What is the average of these 3 numbers?
Standard of one, if you take then
5 to 7 or 10, 17. So it is 5 point something, right? So 5 point something, right? So if you remove this one and find out the average again, So this is 3.5. So 3.5 is definitely less than equal to the previous average. So this is basically intuitively it is fine. So it is asking the same question, deleting a vertex of maximum degree cannot increase the average degree. Is it true or it cannot? It is not true.
True.
And then second one, deleting a vertex of minimum degree cannot reduce the average degree.
Also true.
See, for example, the first one is true. Let's give a average degree vertex. And after that, you can say that, okay, so you are saying that this is true, but okay. So what happened? Let G be an average degree. G has average degree A. X be a vertex in G so that this is equal to delta G. And you have then this is, okay, after that, if you see this first one is true. What about second one? First one is true. That is what the proof. Also, you can get this one. What about second one? Cannot reduce the average degree. Will it be true? For example, if I take this one, what is the average degree of this? What is the average degree? What is the average degree of this graph? 2. 2. If I delete this one, delete this vertex, what is the average degree?
1.
1. This is 1, 1, 1, and 2. 4 by 3, right? Which is less than 2. So cannot reduce the average degree. That is not true, right? This is the counter example. So it can reduce. Is this clear?
Yes,
Yes,
sir.
sir.
Okay. So sometimes, this intuition will not give you, may not give you the correct statement. You have to provide the logic, right? Prove that every graph with n vertices and n edges contains a cycle.
Sir, this is proof that every.
Prove.
Sir, how can prove, sir? We know that, sir, n vertices, then n minus 1 edges contain a cycle.
So n minus 1 edges, then it has no cycle. If the graph is connected and it has no cycle, then n vertices is there, then at most it will have exactly n minus 1 edges, right? So if you use that particular fact, then first you can assume that the graph is connected. If n vertices are there, then if the graph doesn't contain any cycle, then it can have exactly n minus 1 edges. Since it containing n edges, so you are done, right? So when G is connected. What about G is not connected? Then what will happen? At least you have got n1 vertices, n2 vertices, n3 vertices, n1, n2, n3, and n4. At least one of the component you will have greater than equal to n1 edges, right? Everything is less than n1 minus 1, then total number of edges will be strictly less than n. So it is not true. So you'll catch hold of one connected component where n vertices are there and n edges are more than n edges are there. So you can use that same logic to show that this is a cycle. So every graph with n vertices, whether it's connected or not, with n edges, must contain a cycle. Is this clear or no?
Yes, sir. Yes, sir. Suppose if it is connected, then it should be unique cycle, right? It contains unique cycle.
Yeah, it is unique cycle. And otherwise also, how many cycles will be there? Can you have 2 cycles? Yes. For example, 4 vertices, 8 edges, 8 vertices and 8 edges, right? 4 vertices and this is 4 vertices, right? And now if you want to have, suppose you have like this, so this is what, how many edges? 5 edges, and this is 4 edges. 9 edges, but you have got 8, then you can take this one also. So it is basically, you can make one component very dense also by taking isolated vertices. So that is the case. So as I told you, right? So most of the cases, without loss of generality, we may assume connected graph. In this case also, the graph is not connected. You look for a component, and at least one of the component will have equal or more number of edges than the vertices, because each component has less than the number of vertices, then total number of edges will be much lesser than n. So we have a contradiction. So you catch hold of one component which has got more number of vertices, at least, and the number of edges is at least the number of vertices. So now you see the connected graph. So if it doesn't have any cycle, then it should be a tree, and every tree with n vertices has n-1 edges. So we have a contradiction. So it must have a cycle. So that is what you do. Fine.
Yes, sir.
Yes, sir.
Okay. This is what you did in the class, right? So this, kindly correct it. I have not corrected this one. I told you this should be less than equal to, at most, not equal to. Okay.
Yes, sir.
So maximum degree is at most 6. Okay, so this thing you can see, so not okay. So this one we proved, right? If G has n vertices and minimum degree is at least n-1 by 2, then prove that G is connected. This we have already solved. So I don't want to touch. Okay. So this is an interesting problem. A simple graph having no isolated vertex and no induced subgraph with exactly 2 edges. So what are the induced subgraph with exactly 2 edges? How it is going to look like? Induced subgraph with exactly 2 edges. It can be something like this, or it can be something like this. Either this is one possibility, there is another possibility. And graph has no isolated vertex. Degree 1 vertex also is not there. Then prove that G must be a complete graph. Complete means any 2 vertices are adjacent. Right? So how do you go about proving? If possible, the graph is not complete, so there will find x, you'll find x and y, and there is no h. Right? And since it is not isolated, there will be one vertex adjacent to this. Since it's not adjacent, one vertex adjacent to this. If these 2 vertices are same, so this is Z1 and Z2. Z1 is equal to Z2, then what will happen? You will come back to this particular situation, right? So which is a contradiction. If Z1 not equal to Z2, then since this vertex also, if Z1 has to be adjacent to some vertex, if Z1 is not adjacent to some vertex, so you'll get into these cases. Z1 and Z2 are not adjacent, then you will get the cases. Now, if X is adjacent to Z1, then these 3 vertices will now form this situation, K1, 2. If Y is adjacent to Z1, then you are done. So if Z1 is adjacent to Z2, then what will happen? So this is the situation, right? So this is the situation. So Z1 is different than Z2, and Z1 is not adjacent to Y1, and Z2 is not adjacent to X2. So if they are not adjacent, then I can take these 4 vertices of this string, so they must be adjacent. So they must be adjacent. So in this case, I can take these 3 vertices, which is isomorphic to this one. So you have a contradiction. So the graph must be complete graph. Is it clear? Or you have any queries to ask? Yes.
It's fine, sir. Yeah.
Okay. So, anyway, you can go through the all these details also. Okay. I want to show you one problem. What is that problem? Okay. So let us, this is an interesting problem because this leads to the Ramsey theory. Anybody tried this problem?
R33.
R33. Huh? Did you try how to solve that? At least 3 mutual friends or 3 mutual strangers will be there. So let us see this thing. So take a, you can construct this a graph, right? Then in G, whenever this is X and Y are friends, when they are stranger, then there is no age, right? So this age is missing when they are stranger. So only friends, they will be having age. So this is the friend graph, and this complement, G complement will be the stranger graph. So take a person X, take a graph with 6 vertices. This is the complement of that vertex. So in G, suppose degree is equal to 1, it can be what? 1, 2, 3, 4, 5 or 0. So in G complement, what will be the degree of X? In G, degree of X equal to 0, it will be 5. Degree of X equal to 1, that will be 4. This is 2, this is 3. Then 3, it is 2. 4, it is 1. 5, it is 0. So you can make a statement, at least there are each vertex, degree of X in G is greater than or equal to 3, or degree of X in G complement is greater than or equal to 3. So at least the vertex will have at least degree 3 in G or at least degree 3 in G complement. Is this clear?
Yes, sir. Yeah.
Yes.
Yes, sir.
So without loss of generality, because complement of a graph, complement of G complement is G itself. So without loss of generality, this X has degree 3, at least 3. So A, B, and C are the neighbors of X. If they are mutually friends, if any of them is friend, AB is friend, or A and B are friend, or B or C are friend, or C or A are friend, then we got a triangle in G, right? If they are friend, then, so they are stranger in, they are stranger basically. This B, A, B, C are stranger. If any pair is friends, then we'll with X they will form a triangle. So either 3 persons will be friends, or mutually 3 persons will be friends, or they will be mutually strangers. Is this clear?
Yes, sir.
So, so this R33 is equal to 6. That is the minimum number of vertices in a graph which will have either K3 or K3 complement. So RKK is equal to M or R. RKK is equal to say R. If R is the minimum number of vertices in minimum vertices required, so that every graph with R vertices will have a complete graph with K vertices or an independent set with K vertices. Right. So this is the meaning of R. So what is the value of R? So that there is some important open problems. Some bounds are available. For 3 it is solved, but other cases, and then this K and K cannot be, it can be different, K1 and K2. So what is the minimum number of vertices in a minimum vertices required, so that every graph with that many vertices will have either a complete graph with K1 vertices or independent set with K2 vertices. So that is basically Ramsey theorem, Ramsey numbers. and Ramsey number of graphs, but it has got other meaning also. So these are basically some of the important problems. So Professor Sunita, I can stop over here, and then for the students, the participants, I think I have shared this tutorial sheet answers also. You kindly go through it, and then my email, you can reach out in case in future you require to learn or clarify some of the things.
Yes,
All
sir,
right.
yes. Yes, sir. Yeah.
Okay. Anything you want to ask from your side?
Thank you so much.
Anything you want to ask from your side? Then otherwise you stop.
Yes, participants, if you have any query, then you can ask. Otherwise, we have to take
Yeah. So because
Like
other people will be waiting.
5 or 10
Yeah.
minutes, and we have to rejoin for validatory.
Yeah. Okay. So Sunita, I just wanted to say something. See, because I have some other work at some 7:15. I have another meeting. So Sunita, I just wanted to speak you. So you were saying that giving us some feedback, but I don't have time to do. So anyway, so I thank Professor Dr. B.S. Banda for giving this nice lecture. Sir, actually, so this maybe I learned in graph theory point of view, I learned many things, but anyway, this algorithmic point of view, this is new to me. If when I have some queries or something, if I'm going to read the book which you suggested, if I have anything, maybe contact you, sir. Maybe the next year you are saying that the program, maybe I will try to attend the program.
Okay.
Yeah.
Welcome. You can reach out to me through mail or any form, right?
Yeah.
Okay. No
Outset,
issue.
okay. Thank you, sir. Outset, I thank the organizer, Sunita, Dr. Sunita. Thank you very much for giving this opportunity.
So much.
Yeah.
But if you have at least 2 minutes, then please attend. In last, you have to come because the participant feedback is around, I think, 8:30. So you can join if you have some time then.
Yeah. If okay. So maybe I have some other meeting. That's what with my colleague. So that's what I'm sorry anyway.
No. What Professor Sunita is telling that toward the end you can join.
Yeah. And also I thank Professor Srinivasa Kotayada, sir. You are actually, I also thank for especially. I learned from you because of from the theory, number theory, especially for Riemann zeta functions more.
Very good.
Yeah. And one more, our Professor Jigil K. Verma. So I want to say, because that is a new topic to me, sir, actually. So I don't know how to express my thanks to him. But from him, I just wanted to continue my the other things.
But still, you are giving good answers there. So it means you have learned new things.
Yeah, definitely, because those things is matrix analysis. So my matrix group, I didn't know anything, but you are saying something. But anyway, so I learned many things. So I want to learn more also from that. Okay.
Good.
Okay. Yeah.
So,
okay, sir. Thank you very much. Yeah. Okay, sir. Thank you.
So, Professor Bhavani Panda, we sincerely thank you for taking your time and the efforts. Okay, it was wonderful. And as I said in the beginning, Sunita was little biased towards graph theory. Okay.
Yeah, she took a lot of care. In fact, during the lecture. Yeah, good. Of course, that much of affinity has to be there as two graph theories, right?
I hope it has gone into the participants.
But
So, Bhavanida, thank you very much.
Thank you. Welcome. Thank you.
We shall meet soon after this, 5-10 minutes. We will meet again. Yeah. Okay. Bye-bye. Thank you.
Okay, sir. Thank you very much. Yeah. Bye.
Thank you very much.
Ma'am, thank you. We'll meet. Okay, later. Bye.
Okay, sir. And
same link, Sunita, Professor Sunita.
Yes, sir.
Same link or different link?
Same link, sir. Same link. You have to.
Okay, ma'am. Okay, I will contact you later. Okay. Thank you. Yeah.
Okay.
Okay.
Yeah. Okay, Gavaskar. See you.
Okay,
Bye-bye.
sir. Thank you, sir.
Yeah.